All right, let's get started. So, hopefully that wasn't too bad. I also have your quiz 2s to give back, but I'll give those back at the end of class, so someone remind me to end class like 2 minutes early so I can give those back. Because I don't want to hand them back and you're there looking through them instead of paying attention to what's going on here. But we are just going to continue where we left off. Last time we started talking about the idea of a limit. And recall, we write this notation, this symbol, limit as x approaches a of f of x equals L, if what happens? Someone tell me without looking back at your notes. What does this mean? Yeah?
As x approaches a.
As x approaches, or let's say, just to be more suggestive, gets close. Yeah, the word would be approaches. That's how we read it. To a, yeah.
From the left and the right, the function tends or gets close to the right.
Then f of x gets close or approaches L. Okay? Now, the phrase gets close and approaches, that's very important because you don't care about being at the point. So if you have a hole on your function, a limit doesn't care that there's a hole. It's going to give you an answer regardless. So that's basically it. This is, we say the limit as x approaches a of f of x equals L. And when we say that, we mean this. And then this is the symbol that we used to write that down. Now, of course, some remarks. Let me make sure. One, f of x need not be defined at x equals a. So you don't have to actually be able to get to the point. That's a very important thing. A limit is different from just plugging in a point and just computing a y value. And we even did an example here. We found that the limit as x approaches 2 of x squared minus 4 over x minus 2, we found that that gave us an answer of 4, even though technically speaking, this function is not defined when x is 2. Like the limit doesn't care about being defined at the point. Right? It cares about, is your y value getting close to something as your x is getting close to something. We also saw an example where the limit did not exist. So that's another thing. Maybe I should complete the sentence. F need not be defined at x equals a for the limit to exist. And just make notes that limits may not exist. It's possible. So we actually did an example here where we had a function, I believe it was x minus 2 squared, when x was less than or equal to 2, and it was like 3x plus 1, and x was greater than 2 or something similar to that. And I asked what was the limit as x approaches 2 of the function, and we found that that did not exist. And that was because the function kind of looked like that. As you approach 2 from this side, the y value was approaching 0. As you approach 2 from that side, the y value was approaching 7. So I couldn't make the statement that there was some y value that we're approaching because it depends on the situation. So a limit may not exist in that situation when you have competing y values. they also won't exist if we can't get. Now when we say close, what I mean is more specifically arbitrarily close. And in the sense that you should be able to get as close as you want to the number. So for example, if I have a function looking like this, let's say this is at 1, and there's a point over here, let's say that's at 2, then there's a whole gap again, and then the function goes over here, and there's a point over here at 3. Then the limit as x approaches 2 of the function does not exist. Right? Why? Because I can't really get close to 2. There's always going to be some distance that I can't cover as I'm approaching 2. So really in this situation we would say we can approach 2. Once there's some gap between the numbers that we care about approaching, we can't actually take a limit there. So when I say we get close to L, I mean get really, really close to L. In theory, as close as you want, right? So here, we can't get as close as we want. We'll always be a distance of at least 1 away from the point where x equals 2. Right? So that's very important as well. So it's very important that you realize that you don't need to be defined, but you need to be able to get as close as you want. And there needs to be no ambiguity in what your y value is doing, and unless all those things work out, the limit doesn't exist. Now, let's talk a little bit more about limits existing versus not existing. So we're going to relook at one of these examples, and then I'm going to give you some more examples for us to look at. So let's look at this function here. The one I just did is x minus 2 squared, if x is less than or equal to 2, and 3 plus x is greater than 2. Limit as x approaches 2 of our function, we know does not exist. Now, if you try to look at what the spirit of a limit is trying to get at, right? Remember, a limit is just basically talking about the y value. What is the y value doing when the x value is doing something, right? So, it's in some sense you want to describe the behavior of the function. Now, here, the limit does not exist, but it should feel somewhat unsatisfactory that that's the answer to you, because clearly you can actually describe what is going on with the function, right? So this, in this case, it's unsatisfactory to some extent. Because I can really talk about what the function is doing in some real sense. And the thing is, it just depends on basically what situation I'm on, whether I'm coming from the left. Here though, hopefully it's clearly, as x gets close to 2 from the left side, what is f of x getting close to, right? So if I imagine that I'm on the left side of 2, 0. It's clear that the function is approaching 0, right? If I look at the other side, as x gets close to 2 from the right, I can also clearly say what my f is getting close to, which is 7, right? So I can actually describe what is going on around 2. It just means, that I need 2 phrases to do it instead of 1. And that shouldn't stop us, because it's kind of weird for that to stop us. So the way around this idea is to talk about what we call one-sided limits. Now, In a couple semesters, even this is not going to be enough, because once you go into Calc 3 and you're in 3D, you can approach a point from an infinite number of directions. But as long as we're in Calc 1 or 2, there are only 2 directions to worry about, coming from the left and coming from the right. So these are called one-sided limits because you're only concerning yourself with one side at a time. So I'm just looking at the, I don't know if to call this a definition or a notation really, but here's how we write it down. So if you look at this, but you write a plus sign in the power of the number here, this we call the limit as x approaches a from the right. Right? So this means that you're a plus a little bit, right? You can't really say a plus something because we want to get arbitrarily close, but here you get that you're a little bit bigger than a, or larger, I would say. And getting close from the right side. We can also talk about the other one. Here you put a little minus sign in the power. And this is the limit as x approaches a from the left. Is there something talking? Stop talking. Okay. And of course, this is interpreted similarly. Right? So you write that when you're coming from the left. You're a little bit smaller than A, and you're getting close to A from the left side. So this, instead of writing these two phrases, what I could have done here with this example, I could say the limit as x is approaching 2 with a little positive sign, limit as x is approaching 2 with a little negative sign. And this one will be what? 7. This one? So I can make these two separate statements. I can talk about from the left and from the right. So whenever I have this limit symbol without the plus or minus sign, it just means overall in general, the direction you're coming from shouldn't matter. You can talk about the y value. If you're in a situation where you can only talk about the y value without any ambiguities from one side at a time, use the one-sided limits. And here, the following definition is going to be important because it'll help you compute limits, help you to compute limits. So this is something that you should be aware of. The limit here only exists if both one-sided limits exist. And they must be the same, equal. So if coming from one side or the other, they either don't exist or they give you different values, we say overall, this limit does not exist. For the overall limit to exist, from either side, it must exist, and they must actually match up with the answer. So that's going to be an important thing when it comes down to computing limits. So on your next quiz, I'm going to ask you to compute a bunch of limits, and hopefully between today's class and the next class, you're going to learn how to do that very efficiently and very quickly, because I'm going to ask you a bunch of limits, and I'm not going to tell you what technique you should be able to use. You should be able to look at it and figure out what technique you're going to be able to use. And between today and tomorrow, between today and Wednesday, I'll be giving you a bunch of techniques you can use. Okay? So it's very important that you pay attention to every little definition, every little technique and strategy I'm giving you, because it can get confusing. Like when we're talking about one particular strategy, it might look easy, but if I throw a bunch of limits at you and you don't know what strategy to use, if you're not paying attention, it can get quite difficult. So one technique is to look at from either side. If both sides don't agree, the limit does not exist. Any questions on that idea before I move on? Let's do a couple more examples so that I can introduce another idea. So this was a new idea, it's an important idea, the idea of a one-sided limit. Let's introduce some other ideas before I tell you how to compute these. Here's an example. So let's actually look at these, and then I'm going to define some new concepts for you. Let's look at this one. Okay, so what do we think is happening here? Yeah?
The denominator is going to be 0.
Yeah, so?
You can just turn it into x to the negative 1 power.
Okay.
Would you need to turn it into 0 then?
What do you mean? What do you
go?
mean?
Turn it to 0 then?
No, because this means exactly that. These are the same notation. It's just a different notation for the same idea. So here, you're dividing by x. Here, you're still dividing by x. Just because you write it so that it doesn't appear with a division sign makes no difference. Those are the same. Yeah?
You notice that 1 over x is a fraction, so x gets smaller, then 1 over x gets larger. So if x gets infinitely small, so let's say it's 0.00001,
Yeah.
it gets close to as close to 0 as possible, but only from the right. So you would write.
How do you know only from the right?
Because if you do negative, if you approach from the left, it would be negative 0.00001, and then it's going to approach from the left. So, and
Okay.
that would give you 2 different answers.
All right.
So
here's one way you could see that quickly. The graph of 1 over x should be the graph that we know very well. Do you remember what the graph of 1 over x looks like? Yeah. Okay.
on the first quadrant, you have a graph that goes like that, have a curve that goes like that. And on the third quadrant, you have a curve that's reflected over
Right. So that's the situation. So what you were explaining is, if you're getting close from the right, like 0.0000001, the numbers are getting bigger. If you're approaching from the left, like minus 0.000001, the numbers are also getting bigger, but they're negative, so they're moving down more. And so we have this kind of, well, this kind of graph you should have known since like algebra class. But yeah, so now we're in the situation where we're approaching 0. Now it actually matters what side. If we're on the right side, right? So if we're approaching 0 from the right side, what's going to happen is, as x approaches 0 from the right side, our function is approaching, well, how do you say? Infinity, right? So here, your y value is just getting larger and larger and larger. It's getting larger in the sense that if someone were to pick a number, eventually your y value would pass that number, no matter what number they pick. No matter how big that number is, eventually the graph will pass that number. We express that idea by writing down the symbol infinity, which is sort of like a sideways 8. Now, if we're on the other side of 0, so if we're approaching from this side, you realize that as x is getting close to 0 from the left side, your y value is getting close to negative infinity. And that means if anyone were to tell you any negative number, eventually your y value will be below that number. We express that idea by writing negative infinity. So here, infinity is coming into the mix here. So knowing that, what would you say about this? Yeah.
Does not exist.
Does not exist. So that does not exist. Okay. Let's do the same sort of idea here. Someone else tell me what this graph looks like. Yeah, go.
It's kind of the same as the first quadrant.
The first quadrant looks pretty much the same.
And then we flat over
Yeah.
the y-axis.
It'll be a little steeper, but it's pretty much the same before sketching the graph. And then what?
We flat over the y-axis.
Reflect over the y-axis, so this graph looks like that. Now, if we were to ask the same question, now clearly things are still crazy here. The graph is like shooting way up. If I were to ask the question, approaching 0, if we're coming from this side, you realize that as x is approaching 0 from the right side, what's happening to the y value? It's going to infinity. If you do the idea over here, if x is approaching 0 from the left side, what is happening to the y value? It's approaching infinity. Now, infinity is not a number, but we still want to capture that idea that I wrote down over here about the existence of limits, which, if your y value is behaving in a similar way on both sides, we just define that to be the limit. So, in this case, we would say the answer is infinity. Right? And this is more of a definition that we take for convenience. Right? And again, because the limit is trying to talk about how the y value is behaving, expressing that is kind of telling someone how the y value is behaving. It just keeps getting bigger and bigger and bigger. Right? So we'd be able to say that. There are other instances, and I don't know if I'll get to them today, where the denominator can go to 0, and we might even approach an actual number. Right? So we'll see things like that. Another thing that I just want to point out here is just like I mentioned on the first day, division by 0 is a problem. Technically, I want you to appreciate we're not divided by 0 here, we're just getting close to divided by 0. X is getting close to 0. It never actually gets there, it can't get there. And this is kind of showing you that division by 0 is kind of a weird thing. Here, when we get close to divided by 0, we can't tell what's going on. Over here, if I get close to divided by 0, I can say definitely everything is getting bigger. There are other times when we get close to divided by 0, I can say the answer is 5. Like, there's no one answer, right? So if someone were to say, oh, divided by 0, you just get infinity, right? It's not exactly correct, and it's just very wrong to say that. Division by 0 is very tricky. We can't actually do it, and if we get close to doing it, different situations will give us different results, so that's very important for you. Did someone raise their hand? I thought I saw one in the corner. Now, once we start throwing into the infinity into the mix, we get into the realm of infinite limits and limits at infinity. I'll define those shortly after, but before that, let's look at this one. So we already know what the graph of this looks like. And yes, one of the many reasons why knowing how to graph things quickly is important is for problems like limits. There are times when the graph is going to be a very nice way to talk about a limit. What would you say this is?
Be 0.
Okay, so explain your reasoning why the answer would be 0.
Because as x is approaching the infinity, it gets closer to the x-axis, so it gets closer to 0.
Right. So x approaches infinity means your input values are getting larger and larger and larger without bound, right? A billion, a gazillion, a quadrillion, a googolplex, it doesn't matter how big the numbers are, it keeps getting bigger and bigger and bigger. And what you realize is happening to the y value, it seems to be getting closer and closer to some value. That value happens to be 0. Now, we can say here this equals to 0, and I want you to appreciate a couple things. For one, without the limit, that statement is always incorrect. It's never correct to say 1 over x is equal to 0, because 1 over x is never actually 0. You never actually get there. With the limit statement, that is a true statement, right? So I want you to appreciate the limit is weird because we're getting closer to something. Why I'm allowed to say this is equal to 0 is because 0 is the thing that we're getting close to. How do I know that we're getting close to that? Well, if you pick any other number, you'll realize that the graph will get closer to 0 than it will get to that number eventually. So someone can say, okay, what if the limit was a half? Well, there comes a point where the graph is closer to 0 than it is to a half. So a half can't fit the definition of getting close. What about negative a half? There comes a point where the graph is closer to 0 than it is to negative a half. And any other number you pick, eventually there will be a point where your graph will get closer to 0 than it is to that other number. So 0 is the only candidate here, right? I can't pick something less than 0, I can't pick something greater than 0. By process of elimination, 0 is the only guy that makes sense to actually say here. So those are another class of examples that's very important for you to understand on a conceptual level. Let's actually write down some definitions here. So consider limit as x approaches a of f of x equals L. Definition. If L equals plus or minus infinity. Okay, so for example, in this case, we got L equals infinity. We call the above an infinite limit. Definition. If your A is plus or minus infinity, as it was in this situation, we call the above a limit at infinity. So this is a limit, this is a limit at infinity. This is an infinite limit, that's a limit at infinity. Note, a limit can be both. Obviously it can be neither. For example, if I look at this limit, this is an infinite limit at infinity. My input is approaching infinity, so we're going at infinity, and the result is infinite, so this is an infinite limit. This, of course, is a finite limit at infinity, right? Because you approach a number, you approach 0. So those are some important definitions here. Like, I think that covers all the main conceptual ideas around limits that we need to know for Calc 1. So now let's get down to the nitty-gritty. Let's get down to the strategy. If Jhevon throws like 5 limit problems at you, how do you attack them? Right? That's what we're going to talk about. How do you actually compute limits? For one, you need to understand the ideas I just mentioned very well, because a lot of times it will help you get to the answer without even you doing any calculations. Otherwise though, sometimes you have to do some calculations. Now I'm going to tell you how we actually go about doing this. So the title of the next section is Computing Limits. How do we actually compute them? Now, this is something that is true in general, no matter what math class or actually any technical class you're taking, right? When you study a particular topic, you always want to talk about the strategy for attacking that topic, right? Now, if your professor doesn't actually mention the strategy to you, you need to actually go through a bunch of examples and come up with a strategy of your own, which hopefully should be made clear by the lecture. But I'm going to give you the strategy, right? So when you're approaching a random problem of some type, you should kind of have an idea in mind of what's the first thing I'm going to try? What's the second thing I'm going to try? What's the third thing I'm going to try? So for example, when you're in pre-calc and you were learning about factoring, there was a process to factoring. There was a strategy. There were certain things that you tried first, second, and third, right? So if I gave you a random thing and I said, factor this, what's the first thing you actually try to do? Yeah. What? Foil? So what does that mean?
It's like you go with the first numbers, the outer numbers, and the inner numbers, and the last.
Okay. So if I were to give you like, you would foil?
Oh, never mind.
Right. That would be the first step, right? There's a strategy to factor, right? The very first thing you try to do is you try to pull out the common factor. That's the first thing you try to look for. Look for something that's in every single term. Once you find that, you pull it out, and there's a strategy for how you're going to pull it out, which I'm not going to get into. I assume everyone knows pre-calc. The second thing depends on the number of terms you have. If there are 2 terms, you're automatically going to think maybe it's the difference of squares, maybe it's the difference of cubes, maybe it's sum of cubes. If there are 3 terms, that's when you think of FOIL. If there are 4 terms, you think factor by grouping, right? Based on the situation, there are certain things that should come to mind first, second, or third, or fourth, right? Now, for you to be able to master the material, you should have that kind of knowledge, right? Just this kind of overarching knowledge of how you approach a problem, right? So that way, you can go into a pre-calc exam and your professor can ask you to factor anything, and you're never going to get confused. You're never going to be like, well, you didn't do an example like that in class, or blah, 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 right? You're always going to be ready because you know factoring, right? You don't know how to factor specific examples. You know about factoring in general. This is going to make a lot of your classes easier, and it's going to make mastery come easier. That being said, I'm going to tell you the strategy for limits. There's a way, if I give you 10 random limits, and you start working on the first one, there are certain things that you think about first, second, third, fourth. There are certain things you would try in certain orders so that you don't waste a lot of time, right? And so that you would be more likely to get to the right answer quicker than not, okay? So the strategy is going to be very important for limits and for pretty much everything else. So. And that just might be an issue. So if you're in the situation where you feel like when you're in class, you're understanding everything, but you really do bad on all the quizzes, this could be one of the reasons, right? You're reading over your notes and you're paying attention to particular examples, but you're not paying attention to the overall strategy or approach, right? What would happen is then you'd go into a quiz and you'd feel like you have all the knowledge to do something, but you get stuck because you won't know what actually to do in the moment. And so it's like, I have 10 problems, I'm looking at the first one, I have no idea what I'm doing, right? You don't want to be in that situation. To get out of that situation, thinking in terms of strategy is one way to actually do that. Let's actually get down to it, because I'm going off on a tangent here. So, to compute limit as x approaches a of f of x. Okay? So I give you a random limit. Now this could look like anything. A can be anything, f can be anything. Okay? Here's step one. The first thing you're going to do if I throw a limit at you. This is always going to be the first thing you try. Try to actually plug in the number. Right? Now the moment that works, that's going to be your answer. As long as there are no gaps. Right, remember that situation where there was this isolated point, there was a gap between the two? Technically we could plug in that number, but even in that case the limit would not exist. As long as there is no gaps approaching A, this will work. This may work. So that's the very first thing. I give you a random limit. It might look scary. It might have all sorts of crazy functions in it. Do not be daunted. Do not get confused. Do not be like, oh my God, there's a radical and an e to the x in here. What do I do? No. First thing you do, try to plug in the number. It's always going to be the first thing you try. Right? So our first example, which I believe was something like limit as x approaches 2 of 3x minus 1, would fall to this strategy, right? I see that. 3x minus 1, that's a very normal looking function. It's a straight line. It's a polynomial. Polynomials are defined everywhere. They have no gaps or holes or anything. So, hey, just plug in the 2. That's your answer. So this is one kind of limit that you might see. It's going to be the easiest sort of limit that you might see. Now, like as I'm saying, it might not always look this simple. I can give you some that looks crazy, but you're always going to try to plug in the number first, because if this works, it's going to be the easiest way for you to tell. Right? You just plug in the number. That's the limit. Right? Now there's a certain class of functions where this kind of always works, where plugging in the a is always the same as computing the limit as x approaches a. These are called continuous functions, so we'll talk about those in a little bit. But this is one strategy, and it's the first thing you're going to try. Now of course, you're not always able to do this, right? With the 1 over x example, you couldn't do it. You couldn't plug in x equals 0. And there were other examples where you can't plug in the number. But if you can do that, that's the quickest way to get to the answer. Step 2. Now, you kind of move to each new step if the previous step didn't work. That's kind of the idea, right? First thing you look, try to plug in the number. Second thing, if you can't plug in the number, try to simplify it so you can plug in the number. Plugging in the number is so convenient that you try to force it to happen even if it doesn't happen right away. Now, we also did an example like this. This was the example where we had the limit as x approaches 2 of x squared minus 4 over x minus 2. Now, in the beginning, we could not plug in x equals 2 because we would divide by 0, and that's crazy. Jhevon will give you a 0 if you do that. So you can't plug in the number. The next thing to try is there a way to simplify so I can plug in the number? Which in this case there is, because there is a thing called difference of squares, which the top will factor into that. This will cancel. Now remember this, so this function will behave like x plus 2, except if we're at 2, and good for us, the limit doesn't care whether we can get to 2 or not. So as far as the limit is concerned, the limit of this is exactly the same as the limit of that. And now you can get to the fact that that is 4. So the first thing you're going to try to do is plug in the number. If that works, great, that's your answer. If it doesn't work, the next thing you're going to try to do is you're going to try to simplify to plug in the number. And of course, algebra skills come in handy here, right? You're going to need to remember how to factor, and remember how to combine fractions, and remember how to conjugate stuff, and remember all that algebra stuff, simplifying, you're going to need to know that stuff here. You're going to need to be able to look at something and tell that you can simplify it, and then actually execute the simplification when you realize it can be done. One thing I want you to notice here is that, so that's the second step. This is more of a notational thing, but it is important that you adhere to it. Notice that I kept writing the limit until I got to a position that I could plug it in, right? So keep writing. So notice that while I'm simplifying, while I'm doing a certain trick or other trick, I keep writing the limit symbol until I get to a position where, oh, now it's easy for me to take the limit. And at that point, you drop the limit symbol, and then that's your final answer. So notice that there's no limit here because that's the answer. This is the answer. But that's how you're supposed to write out your work. So we couldn't take the limit immediately because plugging in is what I would try, but we can simplify. While we're simplifying, keep writing the limit over and over until you can actually plug in the number. So that would be the second thing you would try. Now here's the third thing. Which we're kind of going to skip over because it's, there are several techniques involved here that I will teach you later on. For now, I'll just call it a special technique. Okay. So there are certain situations where, hey, this isn't a nice form where I can use this trick. And at the moment, I haven't taught you any of those tricks yet, so we'll come back to this. So things like special trig limits, squeeze theorem, things like of that sort will fall in this category. That's kind of going to be the next thing you want to look for. Is there like some special idea or some special category that this problem falls in that it's easy for me to tell the answer based on what I know happens about that general category? Right, so that would be step 3. That would be the third thing I would look for. So we'll come back to that because there are many techniques in here, and I'm going to tell you about some of them specifically that will pop up in Calc 1. So if that doesn't work, you'd have to do step 4. Now steps 4 and 5 can kind of be alternated depending on what it looks like. So this is interchangeable with the next thing I'm going to tell you after this. But if you can't plug in the number, you can't simplify to plug in the number, a special technique doesn't apply, which I'm going to tell you about, then you should try this or the next thing. So the first thing is going to be to use the graph or table of values. Now, table of values is kind of a last-ditch effort. That's when you're really not seeing it. That's like, yeah. But the graph is something that if something is reasonably easy to graph, you should be able to graph it really quickly and see what's going on. And of course, we actually saw this with the last few examples I did. So I'm going to show you both of these, how to actually use the graph and how to actually use the a table of values. So, example here. So if you looked at that, you'd realize, so that shows up on a test. Of course, your test isn't going to have anything that easy, but just as an example. Boom, that limit shows up on a test. First thing I'm going to try to plug in 0. I'm going to realize, can't do that, that would be divided by 0. Okay, second thing I'm going to try to simplify so I can plug in 0. Now, of course, here, rewriting that as x to the minus 1, as we've discovered, doesn't help because it doesn't really mean anything different. There's nothing that I can do to cancel the x in the denominator, so I can't simplify that, right? Now, this does actually fall under a special technique, but we'll skip over that because we haven't discussed those again yet. So the next thing I would try is, hey, I kind of know what the graph of this thing would look like. In fact, I know exactly what the graph of 1 over x looks like. It looks like this, right? Now, me actually sketching that graph now immediately gives me the answer. I can immediately know that this does not exist. And I could know that because the left and right don't agree. As seen from the graph, right? Here, as I'm approaching 0 from the right, this is shooting up to positive infinity. Here, as I'm approaching 0 from the left, this is shooting down to negative infinity. The left and the right don't agree. That's easy to see from the graph. That is my answer. It does not exist. But again, the strategy is important. You don't ever want to get lost in kind of guessing what will work or not. Every limit I see, the first thing I try to do is plug in. The second thing I try to do is simplify. The third thing I try to do is apply a special technique. The fourth thing I try to do, look at the graph. Now there might be cases where graphing is difficult, and in that case you can use a table of values, which is not recommended really. I mean, it's a valid method, but if a Calc 1 student has to resort to plotting a bunch of values, you kind of know they're in their last ditch effort and they couldn't come up with something more creative. Not recommended, but literally if you can't think of anything else, you do this, right? It's the last ditch effort. And why? Because it's computationally intensive to actually do this, and you're not allowed to use calculators. So you're really wasting a lot of time if you actually use this technique. Let's actually look at the technique for this particular example. Like, how would I recognize that does not exist would be that. Let's say hell freezes over and I forgot what that graph looks like. So here's what we would do. So let's look at the table of values. So I'm pretty much going to look at the x values, the inputs, and the y values. Now, ultimately my goal is to get close to when x is 0, and I want to figure out what the y is doing, right? So at the beginning, I don't know what that's going to give me. So what I'm going to do is, because I understand what a limit means, it means as I'm getting close to 0, I want to know what the y value is doing. So what I'm going to do is I'm going to plug in a bunch of numbers getting close to 0 from above, and plug in a bunch of numbers getting close to 0 from below. How many numbers? Well, there's no set requirement. Plug in as many as you need to see the pattern. Right? That's basically the idea, which is why it's very time intensive. Okay? So for something like this, I would say, now remember, you want to get really, 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 really close. So I'm thinking of like 0.001. Then inch away, 0.01. 0.1, maybe 0.5, stuff like that. Right? So you want to get really, really close. Maybe even that's too far. 3 zeros. 2 zeros, 1 0, no zeros, right? You really want to get close to 0, right? Now you'd of course do the same thing from the other side, minus 0.0001, minus 0.001, minus 0.01, etc. Right? Now when you're plugging these guys in, you're going to actually try to see, can I figure out a pattern that's happening over here with the y values? Because that's what the limit is about. So 0.1 means 1 over 10. If I plug in 1 over 10 into 1 over x, I would get 10. Right? 0.01 is 1 over 100. If I plug that into that, I would get 100. 0.0001 is just 1 over 1,000. So if I plug that into that, it's going to give me 1,000. This is 10,000. Plug into that, it'll give me 10,000. Notice what's happening to these numbers. They keep getting bigger and bigger and bigger and bigger. Right? So I notice that as I'm approaching 0 from this side, the numbers are approaching infinity. I can imagine that if I put more zeros in, the numbers are just going to get bigger. Right? They're never going to settle somewhere. They just keep getting, they keep growing. Now, if I go from the other side, this is minus 1 over 100. This is going to give you minus 100. Right? This is going to give you minus 1,000. This is going to give you minus 10,000. Again, I notice a pattern. As I'm getting close to 0 from underneath, the numbers again keep getting larger and larger, but with a negative magnitude. So it turns out that as I'm getting closer to this line from this direction, it's going off to negative infinity. They get more and more negative. So once I realize that approaching this, I get 2 different values, that tells me it does not exist. Right? Any questions on that? So no questions? Guess everyone's getting 100 on next week's quiz. That's good. That's awesome. Okay, so that would be the table of values idea. And like I said, this was a very easy thing to plug in, so that wasn't really hard. But trust me, if this was complicated, you don't want to spend all your time plugging in stuff, working out by hand. Right? You have to be really good at arithmetic to be able to apply this really fast. So unless you're Jhevon Newman, I'd probably stay away from it. Does anyone know who Jhevon Newman is? Anybody? Does anybody know the movie Good Will Hunting? It's like Matt Damon. He's like this super genius. Like was smarter than all the professors at MIT. His mind is just amazing. Jhevon Newman was a real life example of that. There are not many people like that. A lot of people think of math people that way. Oh my God, you must be super smart. No. Like you can go your entire life. You and your son and their child, you can all go your entire lives and never actually encounter an individual like that. Jhevon Newman was such an individual. You should look him up. He's a really interesting fellow. Yeah, so table of values was the other one. Here's step 5. Use the fact that you know how different functions behave. Now, in this regard, let me just mention here, this step 5 is especially useful for limits at infinity. So if you see you're approaching infinity, you might opt for this step as opposed to step 4. But again, like I said, it's kind of a toss-up. Step 4 and 5, really interchangeable here. At that point, just kind of flip a coin and try to do one or the other. So step 5 especially I would use if graphing is going to be really annoying or I don't know what the graph would look like, I would use step 5. If graphing is going to be relatively simple, I would use step 4. And there are cases where graphing is going to be simple, but it might not appear that way in the beginning. You have to do a little simplifying to figure that out. But anyway, let's move on. So, in this regard, the following is useful. Okay, so now I'm going to tell you about how certain functions relate to each other, especially when the input is going off to infinity. So there's the idea, and you're in Calc 1, 2, 3, even Calc 4. These are the kinds of functions you're going to be studying. There's the idea of an elementary function. Okay? Now, an elementary function is one of 6 types. It's either going to be a logarithm, a polynomial, a radical, an exponential, a trig function, or a rational function, or any combination of these with arithmetic operations. So you can add any 2 of these, subtract any 2 of these, multiply any 2, raise one in the power of the other, take a radical of 1, you create another elementary function. These are called elementary functions. These are the only ones we know how to deal with at this level of calculus, right? Calc 1, 2, 3, and 4. Okay, so how these elementary functions behave as you go to infinity, they are actually very different. So, and I kind of mentioned this when we compare 2 to the x versus x squared. Remember when I did that example where I was like, 2 to the x is going to do like this, and then x squared is going to kind of be like, not even trying, right? If you zoom out far enough, right? That kind of idea can be very useful when computing limits. And it turns out we can talk about many other kind of situations like that. So, in terms of non-constant functions, one of the slowest growing functions that we know of is the logarithm. This guy is going to be pretty much on the bottom. Now a polynomial, like x to the a, like x squared or x to the 4th or x to the 5th, something of that sort, is much bigger than a logarithm as x goes to infinity. So what this symbol means here is much larger as x approaches infinity, right? So the kind of relationship that 2 to the x has with x squared would have that with log to the base 2 of x, or with any logarithm actually, right? A log is going to grow so slow compared to a polynomial that the log might as well not even try if you zoom out far enough. If you zoom out far enough, this guy will look like 0 compared to that guy. Right? Polynomials grow a lot faster than logs. And as I mentioned last time, exponentials grow a lot faster than polynomials. Right? So here, I'm assuming a is larger than 1 here. Here, I'm assuming also a is larger than 1. Across the board. Right? So a log will be much, much smaller than a polynomial when you're going off to infinity, and a polynomial will be much, much smaller than an exponential when you're going off to infinity, right? And kind of the next guy in the totem pole here is something called the factorial, which we're not really going to talk about. You'll see that guy in Calc 2. And here's a guy that we might see something very similar to him in Calc 1. But it's like an exponential on steroids. It's an exponential function where the base is also a variable that's growing. Right? So this is the relationship. Guys on the right are much larger than anyone on the left when you're going off to infinity. To the point where, if you're going off to infinity, anyone to the left of you, you can essentially replace them with 0 and it'll work out. Right? They get that much bigger. Right? And within each category, that also works out. So if you're looking at x to the a, this will be much, much smaller than x to the b if your b is greater than a. So that's also true within each class. So if you're comparing an x squared to an x cubed, if you zoom out far enough, the x cubed is going to be so much bigger that the x squared might as well be 0. Okay? Now once you have that idea in mind, certain limits immediately become like super easy. So if I look at this example, so I see something like that. This is a random limit that shows up on an exam. The first thing I'm going to try to do is plug in the number. But what does it mean to plug in infinity? It doesn't even make any sense. Second thing I'm going to try to do is try to simplify so I can plug in the number. Good luck simplifying that. When you get to Cal 2 and you learn about power series, you might be able to simplify that, but it's still not going to be pretty. Step 3 would be to use a special technique. This is kind of like a special technique, but we'll skip over that. Step 4 would be, what does the graph look like? Does anyone know? Otherwise, you can start to use a table where you plug in numbers closer and closer to the guy. But what would be a good candidate for getting close to infinity? Where do you start? Plug in a million. Plug in a billion? Is that big enough to start seeing a pattern? That probably isn't going to work. So now I have this. Now looking at this, I notice that the top is an exponential. And the bottom is a polynomial. And I have the understanding that that guy is much, much bigger. So essentially what I have here is I have a fraction where the numerator is getting much, much larger than the denominator. What happens to the fraction overall? Goes off to infinity. So I can just look at that and know, oh, the answer is infinity. No calculations necessary. I mean, calculations weren't even possible, but you can't do calculations with infinity. Now, again, I still go through the strategy quickly in my head. Try to plug in. Okay, try to simplify. No. What does the graph look like? Oh, forget that. Oh, it's an exponential number. Right? You think in those steps. Eventually, you'll get to step 5, and you'll be like, oh yeah, that's easy.
So then in that case where we have an exponential in the numerator, we could say it's infinity, but what if it's reversed, where we have a smaller?
That is a good question. I was going to ask you some more examples. What about the other way around? What if it were
That would be negative
1 minus x squared over 2 to the x plus 12. Okay, so look at that example. Any guesses as to what the answer would be? Yeah.
0.
0. Explain.
Well, I would say since the exponential is the top part is causing a polynomial and the bottom is an exponential, the exponential outweighs the polynomial. So as you're approaching infinity in the denominator, the number is getting infinitely smaller,
Right.
getting closer to 0.
Right. So when I'm going up to infinity, this guy is like 0 compared to that guy. Right? So the top is like nothing. Here the bottom is getting much, much larger. And this is kind of the same thing that happens with 1 over x, if you notice. The denominator is getting huge while the top is staying relatively small. It's staying at 1. Whenever you have a fraction where the denominator is getting larger and larger and larger, overall the fraction itself gets smaller and smaller and smaller. Now, of course, this will approach 0. Now, I'll talk about this later, but these two, I would call this one top heavy. I'm going to kind of explain more what that means later. Whereas this one I would call bottom heavy. Right? So bottom heavy limits go to 0, top heavy limits go to not necessarily infinity, it could be minus infinity. For example, if I were to just tweak this a little bit to 1 minus x squared, now the answer would be minus infinity. Do you see why? Right, so because this is going off to a positive number and the bottom is going to be a negative number as x gets large. So it's going off to infinity, but it's still a positive divided by negative. So those rules you still have to obey. Right, the rules with signs, positive divided by negative is a negative. Those still work even when we're going off to infinity. Okay? However, just looking at this, I automatically know that the answer is going to be some sort of infinity. And then I pay more attention to the signs and the kind of functions involved to figure out, is it going to positive infinity or negative infinity? But again, technically this is an example. You should be able to look at it and know what the answer is. And for such examples, you writing down this phrase will let me know that you were thinking of the right thing. So as far as showing your work is concerned, for a problem like this, just write down the answer and then write down top heavy. And then I'll be like, okay, they know what they're talking about. If you write down this answer, I'll just like, maybe they guessed. I won't know what they were thinking, right? So I'm gonna like that you show your work on everything that's not a quiz. And so with problems like these, limit problems like these, writing down certain phrases would indicate to me that you were thinking about the right thing when you did it. And it wasn't just a guess or you didn't just copy from someone. But there are these class of limits as well, where just by knowing about how the functions interact with each other, you can tell the answer right away. So, we don't really have much more time. So what I'll do is I'll write down a bunch of examples that will start off next class by going through these examples. You can try to actually try them on your own. So next class we'll start by going through these examples and then I'll start talking about some special techniques, right? Like how would you go through the step 3 in our strategies? Okay, so do these. want you to try those. Yeah.
Good question, have you assigned anything for the platform?
Oh, the online homework? Yes, there are some assignments up. So if you haven't gotten that, the online homework, you need to get it quick. So there's homework up, and I believe I sent out a mass email, did I not? I feel like I did. But if not, I should.
No.
So the homework is due in like a week from now, or something like that. But there is homework. So you want to start it now. If you can at least get a trial version of the online software for the time being, so you can do the homework. But yes, there is actually homework. There were always some problem sets up, but right now I started paying attention to the due dates and I started organizing some, so there are a few. As well as, so yeah, check out the homework, try these for next time, and wait for me to give you back your quizzes. Until then, we are going to end for today.